Hi, in this lecture I'm going to review some problems from chapters 5 and 6. I have written the statement of the problems here. You can write it down and work it out and then come back and look at the solution and see how well you have done. I will leave each of these pages on for a few seconds. You can freeze the frame and write it down and then move forward to the next frame and write all of them if you wish at the same time. Essentially give yourself a self-test and then come back and see how the solution goes. Here is problem 1 and 2. Here are the next 3 problems. Here are the next 2 problems. And finally here is the last problem. Okay, once again I recommend that you sit down and do the problems and come back to compare, and if you see a discrepancy between the two of them, you want to go back to the text and review that section again. Okay, let's go to the very first problem. First problem is use a Riemann sum to approximate the area under the graph of f of x equal to logarithm of x over x plus 1 over the x-axis over the interval where x is between 2 and 5. We want to use 10 panels. We want to use the midpoint rule, and we want to do our calculations to 4 decimal places. I'll set up the sum and leave it to you to actually use your calculator and find out what the value is. So here's our function. F of x is equal to logarithm of x over x plus 1, and x is between 2 and 5. We don't need to have a very detailed picture of this, but it helps to have something. We know that this function is positive and eventually goes to 0, but even that detail is not of sufficient interest for us. Some sort of function like this. So this is f of x. Our region of integration is from 2 to 5. We are taking n to be 10. So this, that means from 2 to 5 we are supposed to split it up to 10 panels. So each panel is going to have a width of, we typically show this by h or delta x if you wish. That is the last point 5 minus starting point 2 divided by 10, and here we get 3/10, or if you wish 0.3. So we are going in steps of 0.3. That means the next point here is 2.3, the next point is going to be 2.6, and so on. Now we are also told to use the midpoint rule. Midpoint rule means we are picking the midpoints halfway between 2 and 2.3. Well, that's going to be 2.15. How do I find 2.15? I'll either average these two or take half of this step size, 0.3, which is going to be so 0.3 divided by 2 is 0.15. That's the half of that. So that brings us to the midpoint. The next midpoint is going to be same step size away from the first midpoint. So the second one, you can just add 0.3 to this. That's going to be 2.45. Okay, so all these points that are obtained by a regular algorithm, they are all separated by the same distance, just the same at 2, 2.3, 2.6, 2.9 are a list of points for you. The midpoints will be 2.15, 2.45, and so on. Now let's go ahead, write our points. So midpoint is going to be 2.15, 2.45. Here are the midpoints. We go in steps of 0.3, 2.75, 3.05, 3.35, 3.65, 3.95, and 4.25, 4.55, and the last one will be 4.85. Why is this the last one? The next one will be 5.15, will be out of the interval we want. Also, how many points we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We wanted 10 panels. We have 10 points, and we are all done. So we are going to write the Riemann sum is going to be equal to size of any of these strips, the delta x is 0.3 times, now I have to take any of these points, plug it in the description of the function I have here, point in any of these things in that, evaluate that, add them all up and multiply by my delta x. So it starts by logarithm of 2.15 divided by, now we are adding 1 to any of these x's that we have. You might as well do it in your mind so that the writing here will be a little bit cleaner. 3.15. The next one is the logarithm of the next number, 2.45, and this one, just do it in your head, that's going to be 3.45, and so on. Logarithm of 2.75 over 3.75. We go all the way. If you want to write it all down so that you can keep track of things, that would be fine. And the last one, logarithm of 4.85 divided by 5.85. Remember, this is always one more than that one, because in this formula we have x plus 1 in the denominator. Okay, by now we are done with 80% of the problem. Next is the being able to use our calculator carefully and efficiently to find this sum. Now each calculator is different. You're recommended to bring a calculator to your exam and just work this out at that level. Okay, I entered these numbers on my calculator and I got that this answer is 0.8100695, and that's a reasonable answer. Now we are going to move on to the next question. Next question is to do something like this in a theoretical fashion. Let's go about this. It was, second problem was finding a limit of a Riemann sum to evaluate an integral. In that case, we want to take n to be just n, and at the end we want to let it go to infinity. At the limit, when n goes to infinity, we are going to find the exact answer, as opposed to here that we had just 10 panels when we got an approximation. We get the exact answer if we use infinitely many panels. Not every problem is easy to handle in this fashion, but these polynomials can all be done, and they all depend on a set of identities like this that we have done in class. Remember, sum of all the numbers from 1 through n is given by this formula. So the first one really means, let me write everything down here so that we have room to work with. X cubed plus x from 2 to 4. So we go down here. We want to do problem 2, integral from 2 to 4 of x cubed plus x dx using limit of Riemann sums. So we are not applying the fundamental theorem of calculus, finding antiderivative and plugging those numbers. That would be, of course, the easy way out, and that's the importance of fundamental theorem of calculus. This is building up to that. So here we go ahead and say we use h or delta x, whichever you like. That is the last point minus the first point divided by number of panels. Number of panels is now n. So each of these things is 2 over n. Now our starting x is just the left point 2. Next point, we are going by this amount to the right of that. So there's going to be 2 plus 2 over n. What does that mean? Just in the previous problem, our step size was 0.3, and every time we are going right by 0.3. In a theoretical setting, you go right by as much as your step size, which is last minus first divided by the number of panels you got, which now is just this expression. We are just using end point of the intervals. We are starting at this, and the next one is that one plus 2 over n. If we could have started at any other reasonable place, we would obtain the same final limit at the very end. That's Riemann's theorem. So x2 is going to be 2 plus 2 of these intervals, 4 over n. x3 is 2 plus 3 steps. That's going to be 6 over n. In general, I need x sub any number. Well, that's going to be 2 plus that many steps. So it's going to be I times 2 over n. And when you go all the way to the end, you will have 2 plus, well, now you have n steps to make, n times 2 over n. This is, of course, just 2 plus another 2 makes 4, and we are at the right end point. Now, I generally recommend that you use right end point. That makes calculations easy. Right end point rule. If you had used the left point or midpoint or any of these things, you get the same answer, but now life is a little bit easier this way. So what is the function we are integrating? Our next step is to plug any of these x's in this expression and get all the resulting items and add them up. This expression here, let me just go ahead and give it a name. The expression in the integral is x cubed plus x. We are supposed to plug any of these things in f and calculate that. Now, depends on how comfortable you feel about this thing. You can just do this thing one by one. That's going to take a long time. What I do is that I take this representative case and plug it here, and then if I let I to be 0, I'll get that one. If I is 1, I'll get that one. If I is 2, I get that one. If I is n, I get this one. So one substitution will handle all the cases. So I say f of xi is equal to, and I put this 2 plus, let's abbreviate to 2i over n. that has to be cubed plus, and then again another x. Now the difficulty in these problems is just doing this algebra carefully and not missing anything in that step. So let me just remind you, how do you cube something? So for example, if you had a plus b, you want to cube it, either you sit down and just cube it, or if you remember the identity, that is a cubed plus 3a squared b plus 3ab squared plus b cubed. So f of xi then, cube of the first thing, that is 8. Or let me write down everything first time and then I write it later. So 2 cubed plus 3 times 2 squared times 2I over n plus 3 times 2 times 2I over n squared plus the last item, which is 2I over n cubed. So all of this is that. How did I do that? I just, instead of a, I have 2, instead of b, I have 2I over n. Use this identity, open this all up. Next, this is 2 plus 2I over n. Now we go ahead and clean this thing up. I'll have 8. This is 24I over n. This is 4 times 2 is 8 again, times this 24I squared over n squared. That is 8I cubed over n cubed plus 2 plus 2I over n. Finally, that is 10 plus 24 and a 2 is 26I over n, and then 24I squared over n squared plus 8I cubed over n cubed. Our Riemann sum is our delta x times f of the first point, f of the second point, all the way to f of the last point. That means I should take I to be 1, that's going to be the first. I equal to 2, that's going to be second. I equal to 3, going to be third. I equal to n is going to be the last one. Again, remember, we are using the right endpoint rule, so we are starting at 1 and going all the way to n. If you wanted to use the left, you would have started at 0, ended up at n minus 1. So this is the right Riemann sum, if you wish. In a sigma notation, this would be delta x times sigma of f of xi, I ranging from 1 through n. So we have, let me just remind you also, by delta x is same as h. Now what is left to do is to actually carry out this summation. How do we carry out this summation? Let me write it down. Our h was, or our delta x was 2 over n, sum of this 10 plus 26I over n plus 24I squared over n squared plus 8I cubed over n cubed. The summation is done from 1 all the way through n. Okay, as you notice, these problems, type of problems, are probably, algebraically speaking, the most demanding of the problems we are going to be doing in this chapter and the next one. And well, you have to make your decision how deeply you want to go into these things. It's really not deep, but it's just the amount of algebra is substantial, and you have to be committed once you get into this. Okay, let's go on. How do we proceed? This is 2 over n. I'm going to split my summation. Here, the first one, I'm adding up lots of tens from 1 to n. So here I write it 10 sigma of 1 I starting from 1 through n. Next one, 26 and n are fixed. I is the number that is ranging from 1 through n, so I just write it 26 over n, sum of I ranging from 1 through n. Next one, 24 over n squared is fixed, and we are summing I squared from 1 through n. Next one is 8 over n cubed, sum of I cubed, I from 1 through n. Next, 2 over n. Now we have to substitute each of these sums. At the beginning of the problem I gave a short hint about this, and just add them up. Here we are adding 1 n times, so what are we going to get out of it? Obviously you have to get n. 26 over n, adding i's from 1 through n times n plus 1 divided by 2, that is this sum, plus, let me remind you, sum of natural numbers from 1 through n is given by that formula. Sum of their squares, again I from 1 through n, is given by this formula. Sum of the cubes from 1 through n is given by this formula. These are so-called Bernoulli numbers. Now, excuse me, Bernoulli formulas. Now we are using them. They are given to us. We're just substituting here. This is 24 over n squared, and this was n times n plus 1 times 2n plus 1 over 6, and here was 8 over n cubed, and this one was n squared times n plus 1 squared over 4. Okay, that's admittedly a big mess to clean up. Once again, it's a decision up to you how deep you want to go into this. I'll do a little bit of simplification inside this expression, and then we take it one step further. Okay, now let's go ahead and open up these items in the parentheses. Perhaps one thing we can do first to do a bit of a cleanup, like n's here cancel out, n squared and n here, 1n here cancels 1n here, n squared and n cubed, 2 n's here cancel 2 n's here. Now I can go ahead and write 2 over n. This is 10n. This 26 over 2, that's going to be 13 times n plus 1. 24 over 6, that is 4 times n plus 1 times 2n plus 1. 8 over 4, that is, excuse me, we still have a factor of n left in the denominator. 8 over 4, that's 2, still have n in the denominator, and n plus 1 squared. You can do one of variety of things here. One of them would be to just open up the parentheses and see what you get. So we'll have 2 over n, 10n. This is the 13n plus 13. This is 4 over n times 2n squared n and another 2n makes 3n. 1 times 1 is 1. 2 over n, n squared plus 2n plus 1. Now I'm going to do term by term multiplication again. 2 over n, 10n, 13n, 13. Divide these terms by n. 4 times 2 makes 8. N squared over n is just an n. N over n is just 1. 4 times 3 is 12. 4 over n times 1 is just 4 over n. So this is that opened up. Here I open it up same way. N and n squared, I get 2n. This n and the next n cancel out. I get 4. And from the last one I get just 2 over n. 2 over n. Okay, now let's collect like terms. 10n, 13n, 8n. That makes 31. And then this one makes 33n. Next we collect 13 and 12. 25 and 5 makes 29, I guess. And next we have 4 over n and 2 over n. We add them up and get 6 over n. One more round. Let's multiply by 2 over n. This makes 66. This makes 58 over n. And the last one makes 2 times 6 is 12 over n squared. Okay, as we said, lengthy calculation. Write Riemann sum for the integral that we had. This integral from 2 to 4 of x cubed plus x dx is this. Now, what is the integral value of the integral? This integral that we want to calculate, 2 to over 4 of x cubed plus x dx. Definition of this integral was the limit of that when n goes to infinity. Limit of 66 plus 58 over n plus 12 over n squared as n goes to infinity. As the number of panels go to infinity, whatever is left, that is really our integral. The way we have developed this thing, obviously these terms here go to 0. This one also goes to 0. All that is left is 66. So the answer, final answer is 66. Of course, fundamental theorem of calculus tells you calculate the antiderivative, plug 2 and 4 in it, and subtract to get 66 in just barely one line, as opposed to all of this. So it's the issue of how deep you want to understand this problem. On the first reading, maybe you want to put it aside, but it's good to go through this exercise once or twice. Now, next set of exercises we were going to take a look at was some straightforward application of fundamental theorem. First one of them was calculate the following definite integral, cube root of x dx from 8 to 27. Now this type of integral actually is not amenable to the calculations that we have done. It requires separate tricks, but it's good that we have the fundamental theorem of calculus. So we don't go for reinventing the wheel and doing everything from scratch. Rather, what we do here is to go ahead and find the antiderivative. So what's the antiderivative of this? You remember we had the following formula. Antiderivative of x to power of n was x to power of n plus 1 over n plus 1 plus a constant. so long as n was a constant other than -1. So our n here is just 1/3. So let me rewrite this. 8 27 x to power of 1/3 dx. Well, antiderivative of x to power of 1/3 is x to power of 1/3 plus 1, and we have to divide by that, so I divide, and this is the antiderivative. In the antiderivative we plug these two numbers. Traditionally it's written like 8 and 27, and then we calculate. So first let's clean this up. This is 4/3. When you flip it over, it becomes 3/4 of x to the power of 4/3. Now I have to put 8 and 27 in that, so that is 3/4 of 27 to the power of 4/3. We might as well factor the 3/4, that is the same, or minus 8 to the power of 4/3. So when you are doing definite integral, we don't need this constant c because it just cancels out. So I have 3/4. So I have to take 27, take cube root of it, which gives me 3, and raise it to the power of 4, which gives me 81. Same with 8, take the cube root of it, you get 2. 2 to the power of 4 makes 16. Okay, 81 minus 16, that's going to be 65. So 3 times 65 over 4. So we have 195 over 4. Okay, so in barely one page, actually most of it could be just pushed into 2 lines. We calculated the integral as opposed to applying all of this. So fundamental theorem of calculus is really a time saver, life saver. It bypasses a lot of calculations. But don't forget the basic definitions, because every now and then this method doesn't work. These problems are rather contrived. If we change the format somewhat, this type of formulas would not be available to us. These are really very rare cases that you can find antiderivative. Most often, real life, you cannot find antiderivative. So we have to be prepared for using Riemann sum. Next problem in this category, problem B, was antiderivative of cosine of theta, integral of cosine theta d theta from pi/4 to pi/3. You remember the antiderivative of cosine is just sine. So this is really sine of theta, in which you have to plug in pi/4 and pi/3 and subtract. So this is sine of pi/3 minus sine of pi/4, sine of 60 degrees, if you remember, radical 3/2, sine of 45, radical 2/2, and all you can do here is just write it like this. I hope you don't make a mistake of thinking that the numerator is radical 1 or anything like that. Okay, next next problem was calculate 1 through 2, 5 plus u cubed over u to power of 4 du. You remember, for calculating, you have to consider calculating these integrals to see how to break it up so that the ingredients will show up on your table of integration formulas. And here we have a very simple method to apply, which just break up the fraction. Simplest type of fraction decomposition, just break it up. What do you mean by that? If you have a plus b plus c over d, you can just do the opposite of taking common denominator. Just break him up to several fractions. That works when you have one item in the denominator. So this can be broken up 5 over u4 plus u cubed over u4 then du. Well, how do we write that? This is a 1 through 2. This is a 5 u to power of minus 4, and the other piece is 1 over u. Well, antiderivative of u to power of minus 4 is covered by the same formula we had here. Just use that. Antiderivative of 1 over u, however, you cannot apply that formula anymore because it makes the denominator 0. It's a separate formula for this. So let's go ahead and apply that one first. 5 is a multiple. I take u to power of minus 4, increase the exponent to minus 3. Be careful on that. Minus 4, if you increase it, you get minus 3. You divide by that. 1 over u, antiderivative of that is logarithm of absolute value of u. Now, absolute value here is not necessary because the range of numbers we have is from 1 through 2. If you are in a positive range, you don't need that. If the range was entirely negative, you needed it. So I just can do away with that. What is left is to apply the two limits, which are 1 and 2. You might want to write this thing a little bit nicer, which is minus 5/3 of u cubed plus logarithm of u. So I plug 2 in this, becomes minus 5. 3 times 8, that's 24, plus logarithm of 2. Now I plug 1 in this. Plugging 1 in this, minus and minus makes plus 5/3 minus logarithm of 1. Now you remember logarithm of 1 is just 0, so we are left with these two fractions. I write 5/3 minus 5/24 plus logarithm of 2. We might clean up a little bit more here. I just take a common denominator, 24. I have to multiply this by 8, so it makes 40 minus 5 plus logarithm of 2. That makes 35 over 24 plus logarithm of 2. So we had to work a bit harder on this problem to get to the bottom of it. Next set of problems are again integration problems with some trigonometry tricks to be applied, and essentially a review of a bit of algebra and trick. So let's go to problem 4. Problem 4, the first one I believe was integral of sine of 2x over sine of x dx. Here is the $64,000 question. What do you do first? Given some complicated formula here, what applies? And really it is the question that cannot be answered in any easy fashion. Integration is substantially different from differentiation and just comes with practice or very extensive software. So here you might remember from your trigonometry that you had an identity for sine of 2x. The whole thing revolves around remembering that or doing a lot of experimentation with numbers until you come up with correct guess. So if you remember, sine of 2x is 2 sine of x cosine of x, so-called double angle identity. Okay, this problem will be easy because all you have to do instead of sine of 2x, write 2 sine x cosine x, and here you have sine x then dx, and sine x is cancel. You can put the 2 outside, 2 cosine x dx. Antiderivative of cosine is sine. You double that for 2 sine of x, and just throw in a constant for good measure. So a problem that looked hopeless at the beginning, by application of this, becomes very straightforward. But again, the question is, how would you remember that? And the answer is, for most part, by just practice in the remembering your trick course. Next problem, it says sine of x over 1 minus sine square of x dx. Well, what identity is it that applies here? Well, you have to look at this thing to see what are available to you. You might remember again from your trick course that 1 minus sine square of x has another name. And what is that? It's cosine square of x. If you take the sine square to the other side, you probably remember it better like that. Cosine square of x plus sine square of x, that is 1. So our first attempt here is to write this sine x over cosine square of x dx. Now you might remember this thing from a table of integration formulas. If not that, then well, we have to go after some other manipulation, which is the following. I can take this thing and write it as sine over cosine times 1 over cosine. And then you have to remember sine over cosine is tangent, and that is secant. Well, what function is it whose derivative is tangent times secant? Well, that is just secant of x. And that finalizes this problem. Problem 3 here is, what is the integral from 1 to 2 of 2u plus 1 squared du? The thing not to do here is to think that you can just simply increase this to 3 and divide by 3. That's the most common mistake on such a problem. Remember, there is a complicated expression inside this parentheses, or just something other than plain u. So what you have to do here is to open it up and then take it from there. 1 to 2 of 4u squared plus 4u plus 1, antiderivative for u cubed over 3 for u squared over 2 and u, and then that has to be done between 1 and 2. So I plug 2 in this. 8 times 4 is 32 third. Plug 2 in this one, that's going to be 16 halves. Plug 2 in this one, that's just 2. And then plug 1 in these things, so I get 4 third, and then a 4 halves, and a 1. So it's better to match terms that have similar denominator first. So 32 minus 4, that gives me 28, I believe. Well, these ones you can simplify. That's 8 and a 2, and here's minus 2 and minus 1. So we have essentially 28 third, and this is 7. So taking common denominator, we typically write the answers like the 28 plus 21 makes it 49 third. Of course, the engineers go ahead and try to convert this thing to a decimal number. In math, we prefer fractions. Okay, that was that problem. Next set of problems are related to application of substitution. So problem 5, A says integrate 5x squared times x cubed plus 5 to power of 10 dx. What substitution works here? We look for an expression whose derivative is around. We have to do this by trial and error, and here is our substitution. U is equal to x cubed plus 5. What gives it away? The fact that x squared, which is a derivative of that, is sitting by. It's not quite the derivative, it's off by a multiple, but we can always fix that up. We differentiate this. Now you have an option of substitution in a variety of styles. I have seen many students follow something like this. They write dx is equal to du over 3x squared, and just substitute. When they substitute, they'll have 5x squared. This is u to power of 10, and instead of dx they write du over 3x squared. Nice thing is that this x squared cancel out. That's what makes it to work. So next step, you have 5 and a 3, which you could put outside. Integral of u10 du, that can be written as u to power of 11 over 11, and then plus a constant. Now you do back substitution. 5 over 33, instead of u, you write what you had, x cubed plus 5 to power of 11. In simple problems, it's possible to guess your answer, but what I want to see is the substitution and calculations of the differentials and all the steps. So try to follow the standard style so that you can do more complicated problems later on. I'll be expecting that approach on the exam. Problem B is asking us to do the following: sine of x over 1 plus cosine square of x dx. Remember, in the previous trig problems that we were doing here, we were looking for some trig identity that helped us. How do we know is a trig identity to be applied or substitution? We really don't. We just do trial and error and see what works. So if you try to look for an identity, we don't have much for 1 plus cosine squared. You can try whatever comes to your mind. Another thing that you might find useful is that this expression has its derivative written here. That gives us an idea to call cosine of x, call it u. Excuse me. Then du becomes minus sine of x dx. Or if you wish to, well, let's continue with the substitution. Excuse me. Cosine of x was u, so I'll have u squared. Here I see sine x dx in the numerator. If you see that, you might as well go ahead and do the substitution instead of making fractions here. Whatever works for you is fine. Here I have my sine x dx, so I just substitute that by minus du. But if you like to write du as, if you like to write dx is du over minus sine of x, take that, substitute it here, that is fine also. Okay, minus du 1 plus u squared. To make sure you're not confused by what I wrote, this is same as 1 over 1 plus u squared du. Now what is that? Again, you have to remember this from the table of integrals. What function is it whose derivative is this? That was tangent inverse of u. What we have to do is to substitute for u, back substitution, minus tangent inverse of, instead of u I write cosine of x plus a constant. We see that that innocent looking expression here gave rise to an expression for its antiderivative, rather unfamiliar looking function. Next problem, a bit more challenging than the ones we have done. That is problem 5c. Says integrate x squared 1 minus x dx. Well, again, main thing is just a starting point. What do we do very first time? This being a substitution problem, one of the candidates for substitution is a radicand. Take u to be 1 minus x. Well, du is easy. Minus dx, they are just off by minus. Now you have to be aware of an extended substitution here. Let's see what happens. For denominator I have radical u. For dx I have minus du. What should I write for x squared? What does x squared go to? Okay, problems we have done so far were rather elementary. Sometimes you have to pay attention to the following, that you need further substitution. From here you can say x is equal to 1 minus u. Is that right? X is equal to 1 minus u. So x squared is 1 minus u squared. So that's what we are going to do here. So 1 minus u squared. Now I go ahead and open this up. I put numerator is 1 minus 2u plus u squared. Denominator is u to power of 1/2, and here I have minus du. Let's multiply it out. 1 over u to the power of minus to power of 1/2 is u to power of minus 1/2. Let me do step by step. This is, we are doing again fraction breakup. Do this division, and then this division, and then this division. 3 divisions. So 1 over u to power of 1/2 minus 2u to power of u to power of 1/2 plus u squared u to power of 1/2, and all of this is multiplied by minus du. So 1 over u to power of 1/2, just use rule of exponent, u to power of minus 1/2. Let me include this minus inside this, so we clean this up. Minus times minus makes plus. I'll have plus 2u, u divided by u to power of 1/2. You have to subtract the exponent. Exponent here is 1, exponent here is 1/2. You subtract them and you get 1/2. Finally, bringing this minus here as well, and 2 minus 1/2 makes 3/2. Okay, I have all of my ingredients. Du, I go ahead and integrate. Minus, I have to increase this by 1. It gives me 1/2. Divide by what I got, plus 2. Increase this by 1. That gives me 3/2. Divide by what I got, minus. Increase this by 1, it gives me 5/2 divided by 5/2, and then a constant. Now, two more things. You have to do a back substitution, also clean up these fractions. So this becomes minus 2. U, remember u was 1 minus x, so I put 1 minus x to power of 1/2. Flipping the fraction here, I get 4/3. 1 minus x to power of 3/2. The next fraction is minus 2/5. 1 minus x to power of 5/2 plus a constant. So you notice that a few more steps were required here compared to the previous one. Okay, I guess I'll include the other 3 questions on another video so that the videos wouldn't be too long. So you go ahead again, practice the problems on your own, and then view the other video. Good luck and God bless.